Hello, everyone. My name is Wing. Today, I will be presenting my work on a large-scale longitudinal study of flaky tests. This work was done by me along with my collaborators, Stefan, Anjiang, Tao, Darko, and Jonathan. So let's start by understanding what a flaky test is. A test is flaky if it can pass and fail when you run it in the same test scenario. Test scenario in this case being the code under test, the test code, and to the best of the developer's knowledge, the environment in which the tests are run. The problem with flaky tests is that developers would write some code, a server would then run some tests and return the results of those tests back to the developer. If some of those tests fail, then the developer would generally go and debug the fault in the changes that they recently made. The problem, though, is that in the presence of flaky tests, the failures may not actually indicate faults in the developer's recent changes. And because of that, it reduces the developer's trust in testing. Flaky tests may also waste the developer's time, particularly because developers may be misled to debug non-existent faults in their recent changes. Because of these problems with flaky tests, many organizations recently have reported their problems with flaky tests, specific organizations such as Microsoft, Mozilla, Facebook, and Google. So let's take a look at an example of a flaky test. The example shown on the slide here is from the project Wikidata Toolkit. Some things to note about this test is that this test contains over 70 lines of code just in the test method body of this test. The test itself is aimed to actually set up a mock directory, dump some data into the mock directory, and check for its contents. What's particularly important here is at line 2. In the sense that what it would do here is that it may throw an IO exception depending on the order in which the tests are run. Consider this other test that I've added to the slide now. I've abbreviated as T2. If I actually run the test order in T1 and then T2, I would actually see T1 in this case fail. On the other hand, if I run T2 and then T1, both tests would pass. The reason for why this is that at line 7, it would actually create a mock directory in the same path as what the line 2 would have created the mock directory at. And at line 7, that extra true argument would actually set up the mock directory so that T1 can actually pass. So having flaky tests like the one I just showed is quite undesirable. And because of this, some software organizations such as Mozilla and Netflix are already running some tools, what I refer to as detectors, to detect these flaky tests as soon as possible. The idea is that once these tests are detected, they can then be fixed and accommodated as soon as possible. So recent work has actually suggested many different detectors that fall into 3 main types. Namely, they rerun tests while isolating the tests from one another. They rerun tests while changing the order in which the tests are run. And they would rerun tests while changing the underlying implementation of an underdetermined specification. For an example, the iteration order of a hash set. The good news is that all of these detectors are shown to be quite effective at detecting flaky tests. However, the bad news is that these detectors are still quite costly to be applied all the time, especially when many developers have already expressed desire to decrease the testing time already. And reruns from these detectors are just too costly to be used all the time. Essentially, the problem that we now have is that we want to minimize the high cost of these detectors while maximizing the likelihood to detect these flaky tests as soon as possible. To help with this problem, we consider what if detectors were applied only on certain changes. Particularly, we don't always run them, but we smartly apply these detectors at certain changes. So for an example, Mozilla and Netflix have already been applying these detectors only when tests are newly added or directly modified. Because of that, they're actually running detectors now much less than running them on all changes, which is great. But one thing that's unclear is how effective would that actually be at detecting these flaky tests as soon as possible? Namely, we want to know how often are flaky tests already flaky when they are added or directly modified. So this specific question essentially leads into the contributions of my work. Specifically, the goal that we have is to understand when flaky tests become flaky and its implications on when detectors should be run. In order to help with this goal, we empirically studied 3 main research questions. The first one is how effective are detectors if they are run only when tests are added. The second one is how do these different flaky test categories affect the effectiveness of running detectors only when tests are added. And finally, we study when should one actually run detectors. Before I dive into the results of my study, let's first understand how we set up the study. So imagine we have the following timeline for the project of each flaky test. On the left-hand side here, we have the old commits of a project. And on the right-hand side, we have the newer commits of the project. What's particularly relevant for each flaky test is the test introducing commit, which is the commit in which the flaky test was actually introduced. We have the flakiness introducing commit, which is the commit when the test first becomes flaky. And this commit may or may not be the same as the test introducing commit. And finally, we have the latest commit, which is essentially the commit in which we kind of detected this test to be flaky. So in order to accomplish our goal, we use a 4-step approach where the first step would actually be to find the flaky test at this latest commit. We then categorize the flaky tests at this latest commit so that we can study how these different categories of flaky tests would affect the results of our study. We then check for each of these tests when they were actually introduced, whether or not they were flaky then. And finally, for the ones that aren't flaky when they were introduced, we go and find the commit in which the test actually first became flaky. So to understand how each of these steps work, let's first start by focusing on step 1. For the goal of step 1, we're trying to find these flaky tests in the latest commit. And in order to do this, we use 2 different tools to find them. The first one is ID flakies, which is a tool from our prior work that randomizes test orders. We also use non-dex, which is a tool that changes the underlying implementation of an underdetermined specification. When we focus specifically on ID flakies, it's great because it can detect 3 different categories of flaky tests for us. Namely, it can detect order-dependent brittles, which are tests that fail when you run them in isolation, but they pass when you run them after some specific tests. So the example that we showed earlier is actually an order-dependent brittle. ID flakies can also help us detect order-dependent victims, which are essentially tests that pass when you run them in isolation, but fail when you run them after some specific tests. And finally, the reruns that ID flakies does can also help us detect non-deterministic tests, which are essentially tests that non-deterministically pass or fail with no changes to the test order. On the other hand, non-dex can detect 2 main categories of flaky tests. It can detect implementation-dependent tests, which are tests that depend on a specific implementation of an API, whose specifications emits other implementations. Again, the iteration order of a hash set, in this case, wouldn't actually tell you how the implementation would be done, and so it would actually allow other implementations. Non-dex would also rerun tests, and because of that, it can again also help detect non-deterministic tests, which are again tests that non-deterministic pass or fail with no changes to the test order or the implementation of the test dependencies. On the other hand, our goal for step 2 is to actually categorize and confirm if a test is actually flaky. And so in order to control the machine cost to run these tests and the human cost to inspect these tests for this goal, we don't actually use ID flakies anymore, because ID flakies uses these random orders, which actually may miss a confirmation of a test as flaky, which is particularly relevant to our study here. In order to replace ID flakies, we use 2 main tools. The first one is isolation, which is essentially running every test by itself, and that can help us detect order-dependent brittles, which are again tests that fails by themselves, and non-deterministic tests. We also use 1 by 1, which is essentially the idea of running every test before a flaky test. And this again is very helpful to detect order-dependent victims, which are tests that fail when run after another test, or sorry, when another test runs before it. And it can help us detect non-deterministic tests. So overall, with all the steps that I just discussed, our final study setup is shown here. Namely, we first find flaky tests with ID flakies and non-dex. We categorize the flaky tests with 3 different tools. We then check if the tests are actually flaky when they're introduced, again, with the same three different tools. And finally, we find the commit when these tests first become flaky. Using the four-step approach, we apply it on a set of projects. Specifically, we use 68 popular Maven-based Java projects available in a public dataset from our prior work. We apply ID flakies and non-dex to them and detect 684 flaky tests. Note that some of these flaky tests couldn't actually be evaluated on the test introduce and commit. The reason for why is, for an example, because Maven couldn't actually compile these projects due to some dependencies already being unavailable for those versions. But in total, we still had 245 flaky tests that were evaluated on their test introduce and commit. So using these 245 flaky tests, let's switch back now to the research questions. Namely, we wanted to know the effectiveness of detectors when we apply them on only newly added tests, and how different flaky test categories would affect the effectiveness of these detectors. So what I've shown here on this slide is the breakdown of whether these 245 flaky tests are flaky on their test introduce and commit. What's particularly relevant here is our results show that 75% of flaky tests are flaky when they are newly added. We also find that order-dependent victims are the least likely to be flaky at test introduce and commits. Our manual inspections from these finds that these test introduce and commits of order-dependent victims are often actually missing the tests that would actually cause the order-dependent victim to fail. Nevertheless, our implication here is that running these detectors on newly added tests is quite effective. Specifically, it can detect 75% of the flaky tests in our study. But one remaining question here is, what about the 25% of flaky tests that couldn't be detected? Are they actually flaky at the test introduce and commit? And if so, how could detectors detect them as soon as possible? That essentially leads us into our third research question, where we actually manually inspected all 61 of these flaky tests to find the flakiness introduce and commit. Our inspection finds that all 61 of them are indeed not flaky when they were introduced. And for each of these tests, we then record the number of commits that was between the test introduce and commit and the flakiness introduce and commit, and the files that were changed in between these two commits. So now let's revisit the example that we looked at earlier. For this example, we actually find that the flakiness introduce and commit is 522 commits after the test introduce and commit. We've also find, though, that only 30 of the commits made some change to the flaky test class. We also find that the flakiness introduce and commit itself made changes to the flaky test class, the other test classes of the project, and the code under test. Essentially, if actually a developer were to run detectors, when a test class is modified, they would still be able to effectively detect this flaky test. In fact, when we consider all 61 of the flaky tests that weren't flaky when they were introduced, we find that 24 of them actually become flaky when their test class is modified. Essentially, the implication that we have here is that if one were to run detectors only on newly added or directly modified tests, they can actually increase the amount of flaky tests that they detected to be up to 85%. For the remaining 37 tests, where their flakiness introduce and commit changes other test classes, code under test, or build configuration files, we don't really find a clear cost-effective way to detect these flaky tests. But one thing to note is that running detectors infrequently based on the developer's budget can actually help. In fact, we do find that there is a median of about 144 commits that are between a test introducing one and a flakiness introducing commit for these 37 tests. The implication that we have here is that running these detectors every about 150 commits could be beneficial for developers. So overall, we see that some software organizations, such as Mozilla and Netflix, are already running detectors to detect flaky tests as soon as possible. Yet these detectors are still very costly to be run very frequently. In order to minimize the high cost of detectors while maximizing the likelihood to detect flaky tests as soon as possible, organizations are already running detectors on only newly added or directly modified tests. Our study provides the following implications to help. Namely, running detectors on only newly added tests can effectively detect 75% of flaky tests. Running detectors on only newly added or directly modified tests can detect up to 85% of the flaky tests. And the remaining flaky tests can be detected by the infrequent use of detectors based on the developer's budget. For example, they can run it about every 150 commits. So in the process of our study, we've also now built a data set of when flaky tests first become flaky, and all of this is now publicly available online. Besides the work that I presented today, I do want to briefly mention that I will be on the job market this upcoming year and that I have a number of other work on flaky tests. Please feel free to approach me if you're interested in hiring.